Hey guys, now we shall see the concepts of utmost importance such as methods of irrigation, water requirements of crops, Kennedy's theory, Lacey's theory, analysis of gravity dams, theories of seepage, canal drainage works, cross drainage works, canal fall, and what are the various structure of canals that are coming under irrigation engineering by answering 10 questions. Now we shall get into it. Now we shall see the first question. The time required to irrigate a strip of land of 0.4 hectare in area from a tube well with discharge Q value as 0.02 Q max, that is meter cube per second, infiltration capacity or infiltration rate as F is equal to 5 centimeter per hour, and average depth Y is equal to 10 centimeter is. So here we have to calculate the time required to irrigate a strip of land. So this type of or method of irrigation is border irrigation, and we have to find the time required to irrigate a strip of land with the given data. So there is one formula to find the time required to irrigate a strip of land in case of border uh, flooding. So that formula is given as T is equal to 2.303 Y by F log base 10 Q by Q minus FA. So we have all the data like Y average depth is 10 centimeter, F is 5 centimeter per hour, and Q is 0.02 meter cube per second, and area is 0.4 hectares. We have to substitute in the relevant units to satisfy the dimensional equilibrium so that we can get the answer for time in minutes, like option C 39.06 minutes as the correct answer. And if you want to find the A max, that is area of maximum or maximum area to be irrigated, then formula to be used is A max is equal to Q by F. So this is the most important formula regarding border flooding or strip irrigation. And we shall now see various types of irrigation or systems of irrigation. So there are two systems, lift irrigation and flow irrigation. Lift irrigation will be done by pumping, that will be done by manual or animal power, or we can use mechanical or electric power. And flow irrigation by gravity. So there are two methods, inundation or flooding, we can say. Perennial irrigation. In perennial irrigation we have direct irrigation and indirect irrigation. For example, in direct irrigation we use uh, hydraulic structures such as weir, barrage, and river regulators. In indirect irrigation, we use hydraulic structures such as dams. And we shall see one by one the methods and types of irrigation. So first one, subsurface irrigation. This subsurface irrigation will be used when the soil is of highly permeable type. And next we shall see the border flooding, when area is leveled in direction perpendicular to the flow in order to prevent water from concentrating on either side of the border. So the diagram which was shown in previous will be conformed to border flooding. So when the area is leveled in direction perpendicular to the flow, so that so that we can prevent water from concentrating on either side. So this technique is followed in border flooding. And next is the check flooding. We will construct the check bunds that will be along the contours. And next is the basin flooding. Basin is nothing but like ponding, we can say. So that will be that method of flooding or that method of irrigation will be used for growing orchards. Orchards means some like fruit growing trees. And next is the furrow method. Furrow method will be used for sugarcane, groundnut, potato, tobacco. These like crops will be grown with the help of furrow method of irrigation. And next is the sprinkler irrigation. Sprinkler irrigation has the maximum water application efficiency, that is 80% water application efficiency comparing to all other flooding. Inundation has a very less water application efficiency. And next is the drip irrigation. This is best suited for row crops or orchards. So these are some important points regarding systems and methods of irrigation. Now we shall move to second question. So before moving to second question, we shall see this graph. Like in drip irrigation, the graph is like in all the time, the field capacity is not fluctuating; it is constant. But in case of surface method or flooding or inundating method, the field capacity will be fluctuating rigorously because water application efficiency is very low. But when compared with sprinkler method, water application efficiency is somewhat higher, like 80% we have seen. So that's why fluctuation is somewhat low when compared to surface method. So this is the moisture content axis. This is the days. In all the time, in case of drip irrigation method, there will be less fluctuation in field capacity, and therefore, and next will be sprinkler, and in the last, like inundation method, surface method has the large fluctuation. So now we shall move on to second question. So moving to second question. So they have given some data regarding concentrations of sodium, calcium and magnesium ion concentration. As 345 milligram per liter for sodium ion concentration, 60 milligram per liter for calcium ion and 18 milligram per liter for magnesium ion concentration. So we have to find the sodium absorption rate value, that is SAR. So we have to use one formula regarding SAR, that is sodium absorption ratio, to calculate the SAR value by using the given three concentrations of ions. So here the answer is option D, 10. So now we shall see the formula, like SAR is equal to Na plus divided by root of Ca2 plus magnesium ion divided by 2. So here we have to note the concentrations of ions has to be in milliequivalent per liters. But in the question they have given us what? Milligram per liter. But in the formula we have to substitute in milliequivalent per liter. That is the main point to be noted here. So how to convert milligram per liter into milliequivalent per liter? Just by using the atomic weight of the ions. So Na plus atomic weight is 23. That is what? Sodium atomic weight is 23. So that's why 345 divided by 23 gives the answer as 15 milliequivalents per liter. So in case of calcium, atomic weight is 40, but there are two valencies. So atomic weight divided by like valencies, like 2, 40 by 2, so 20. So that's why 60 by 20 equal to 3 milliequivalent per liter for calcium ion. Similarly, in case of magnesium, we have 24. So that's why two valencies are there. Two valence electrons are there. So that's why 24 by 2, 12. So 18 by 12 gives the answer as 1.5 milliequivalent per liter. So this is how we have to convert milligram per liter into milliequivalent per liter and then substitute the values in this formula. SAR is equal to Na sodium ion divided by root of calcium ion plus magnesium ion divided by 2. All things in milliequivalent per liter. And next we shall see another formula regarding salinity concentration. So this will be given by Cq divided by Q minus of Cu minus Re. Here C, we know the concentration of saline, like saline concentration. Q is the discharge in Qmax or anything relevant units. C is the consumptive use and Re is the useful or effective rainfall. And this salinity concentration shall not be more than 2000 ppm. So we shall see the range, and so that we can classify how the water we are using in the irrigation. If the water has SAR of range 0 to 10, then we call it as low sodium water. When the water has SAR of range 10 to 18, then we can call it as medium sodium water. That will be denoted by S2. In case of 18 to 26, we can call it as high sodium water, S3. In case SAR is greater than 26, then we shall call that irrigation water as very high sodium water, which will be denoted by S4. And how we have to classify with respect to salinity concentration? Salinity concentration, that is C suffix S, is proportional to electrical conductivity, that is EC. Electrical conductivity will be given in micromoles per centimeter, and the range as follows. If it is less than 250, then we can call it as low saline water, that is denoted by C1. And if it is of range 250 to 750 micromole per centimeter, then medium C2. 750 to 250, 2250 or 2250 high salinity water. In case more than 2250 micromole per centimeter, then very high saline water, that is C4. So this is how we have to classify the irrigation water, and we have to select that water to the requirement of crop, or else the crop will be damaged. We shall move on to third question. So third question, in a cultivated area, soil has porosity of 45% and field capacity, that is FC, 38%. For a particular crop, root zone depth is 1 meter and PWP, that is permanent wilting point, is 10% and consumptive use is 15 mm per day. Irrigation efficiency is 60%. What should be the frequency of irrigation such that moisture content shall not fall below 50% of maximum available moisture? So they have given many data. You can pause the video and try to get the answer. We have to use some 2 to 3 formulas to find the answer for frequency of irrigation such that moisture content shall not fall below 50% of available moisture. So here the answer is option B, 6 days. Now we shall see the calculation part. So first we have to know the given data. What are the given data? And we have to denote with respective symbols like porosity as small n 0.45, that is 45%, field capacity 38%, PWP per wilting point 10%, D is equal to 1 meter, that is root zone depth as 1 meter, consumptive use is 15 mm per day, and D naught, that is readily available moisture, or we can say in that way also, that is nothing but 50% of D available. And we have to use these two formulas to get the answer. N by Fc is equal to gamma S by gamma W. So what is N here? N is porosity, Fc is field capacity, gamma S is unit weight of soil present in the ground level, in the present below the ground, and gamma W is unit weight of water. So here they have given N and Fc only. There is no mentioning about gamma S. So we have to use this relation to get gamma S by gamma W. That is N by Fc. So we know N, we know Fc. So we got gamma S by gamma W. Just substitute here this value. And D we know root zone depth 1 meter and Fc is 0.38 and PWP is 0.1. So on substituting all the data in this formula, we will get the answer for D available. But they have mentioned as the moisture content shall not fall below 50% of maximum available moisture. So by now we have calculated the maximum available moisture depth as D available, and we have to calculate the readily available moisture, that is D naught, as 50% of D available, so that we can use that value in frequency, that is D naught by Cu. So D naught by Cu gives one answer, that is nothing but 6 days. So this is how we have to calculate the frequency. So we are using here some 3 4 formulas. One is readily available moisture, another one is this relation N by Fc is equal to gamma S by gamma W, and available moisture content depth as D available is equal to gamma S by gamma W D into Fc minus PWP, and then finally frequency as what, D naught by Cu. So this is how we have to proceed with this type of question, like moisture content depth. Now we shall see other thing apart from that. One is irrigation requirement and another one is irrigation efficiencies. So first we shall see the irrigation requirement. So there are 4 irrigation requirements, that is a consumptive irrigation requirement, net irrigation requirement, field irrigation requirement, and grass irrigation requirement. So this is how the order follows in the ascending order. The least is the consumptive irrigation requirement. Consumptive irrigation requirement is equal to Cu minus Re. Cu minus Re. Like Cu is consumptive use in mm per day or something else. Re is effective rainfall or runoff. So Cu minus Re gives the consumptive irrigation requirement. And what about NIR? NIR is nothing but summation of CIR, LR, and PSR, and NSR also, anything else. So expansions of those like LR is nothing but leaching requirement, PSR is pre-sowing requirement, NSR is nursery sowing requirement, plus CIR gives the net irrigation requirement. And next is the FIR, that is field irrigation requirement, that is nothing but NIR divided by application efficiency. Water application efficiency is denoted by eta A. So NIR divided by eta S gives the answer for FIR, that is field irrigation requirement. And the greatest value is gross irrigation, that is nothing but FIR divided by what? Conveyance efficiency, eta C. So these are the some basic formulas and concepts in irrigation requirements. First one is CIR, that is consumptive use, NIR net irrigation requirement, field irrigation, and gross irrigation requirement. So here itself I have mentioned all the things. CIR is CU minus RE, NIR is CIR plus LR plus PSR, FIR is NIR divided by application water application efficiency, and this is conveyance efficiency. And now we shall see the points regarding irrigation efficiencies. There are four things. One is conveyance efficiency, application efficiency, water use efficiency. Last one is depth efficiency or distribution efficiency. So first is the conveyance efficiency. So water conveyance efficiency is given as the ratio of quantity of water delivered to the fields to the quantity of water diverted into the canal system from the irrigation. So that means what? Whatever the water we have delivered to the field actually, but to the ratio of quantity of water diverted to the canal system from the irrigation. So that is how conveyance efficiency will happen. So conveyance efficiency is the ratio of what quantity of water diverted to the field to the quantity of water diverted to canal system for the from the irrigation purposes. And next is the water application efficiency. This is nothing but the ratio of quantity of water stored in the root zone of the plants to the quantity of water diverted to the field. So whatever the quantity of water we are diverting to the field, that will be stored in the root zone. So, but there will be some losses in the application of the water into the root zone. So that's why water application efficiency comes into picture. And next is the water use efficiency, that is eta U. So that will be given as the ratio of quantity of water used beneficially to the quantity of water delivered to the fields. So all the water cannot be used beneficially. If at all efficiency is 100% of, that is water use efficiency is 100%, then that means whatever the quantity of water diverted to the field is actually used totally. So that means water use efficiency is 100%. But there may not be achievement of 100%. So that's why efficiency of, that is water use efficiency, may be less than 100%. So this includes water required for leaching. So water use efficiency includes the requirement for leaching purposes, leaching requirement. And at least, and the last one is water distribution efficiency. So that will be given by using this formula. This formula is important regarding water distribution efficiency, 1 minus y by d into 100. Here y is the average numerical deviation in depth of water stored. Average numerical deviation in depth of water stored, where small d is the average depth of water stored in the root zone during irrigation. There are many depths. We have to calculate the average among the all depths, that is denoted as small d. And y is the deviation of all depths. For example, d1, d2, d3 are there. We have to calculate the average. So we will sum it up and divide by 3. So that is denoted as small d. And in case of y, that is deviation, that is nothing but d1 minus d modulus value. We have to consider only the positive. And plus similarly d2 minus d plus d3 minus d divided by 3. So that is the average numerical deviation of all depth of water stored. So this is how we have to calculate the water distribution efficiency eta d. So these are some concepts apart from this problem, that is irrigation requirements and irrigation efficiencies. Now we shall move on to fourth question. So fourth question is the most important one, relation between duty and delta. In many examinations, we see this relation based questions, duty and delta. So option A, B, C, D. Which one is correct? So option A is correct one. Delta is equal to 8.64 B by D. We shall see elaborately this formula now. Del is equal to 8.6 B by D, where B is base period in days. Units are important here. Base periods has to be in days, delta should be in meters, and duty is in hectares per Qmax. This data, like these units, are to be followed empirically. We cannot use other units. Base periods shall be in days. Delta, that is depth in meter, and capital D, that is duty in hectares per Qmax, hectare per discharge, 1 meter cube discharge, we can say. And there is one important thing called crop period and base period. Crop period will be always greater than base period, because crop period is the total time period from the instant of sowing of the crop to the instant of harvesting of the crop. So that is the total time period of which is called as the crop period. But base period is the total time period from the first watering done for the preparation of land to the last watering done before harvesting. So watering time is the base period, sowing time is the crop period. So that's why crop period is greater than base period. So this is one important point regarding crop period and base period. And we shall see other important terms that are coming under like duty and delta calculation. First one is the command area. Command area is nothing but the area which can be irrigated by the canal system. So that is the command area. And GCA is gross command area. This is the total area which can be irrigated by a canal, so that unlimited quantity of water is available. And next is the culturable command area. So this is that portion of grass command area which is culturable or cultivable. This is self-explanatory with the point, with the term. And next is the paleo irrigation. Paleo irrigation is nothing but watering done prior to sowing. That is the paleo irrigation. Paleo irrigation is the watering done prior to irrigation, or sorry, prior to the sowing of crops. And next is the core watering. Core watering means first watering done after the plants have grown a few meters high. When the plants have grown some few meters high, we are watering that plant. So that first watering after the plant has grown few meters high or few centimeters high, then that will be called as core watering. And next, capacity factor. This is the average. This is the ratio of average supply discharge of a canal for a certain duration to the maximum discharge capacity of a canal. So ratio of average supply discharge to the maximum discharge capacity. That is the capacity factor. And next is the time factor. Time factor is the number of days canal has actually run during a watering period to the number of days of watering period. So canal has actually run to the number of days of watering period. That is the time factor. And next, the crop ratio. That is nothing but Rabi Kharif ratio, and other things like outlet factors, crop calendar, etc. There are many things or many terms regarding crop or water requirement of crop. Now, apart from that, we shall see what are Rabi crops and Kharif crops. Rabi crops are grown in winter season, that is October to March. So these are some examples of Rabi crops: wheat, barley, gram, pea, and mustard. And Kharif crops are grown in monsoon season, April to September. And here examples are rice, jowar, bajra, jute, and groundnut. So these are basic things regarding Rabi and Kharif crops. And we shall see, apart from that, we shall see also the classification of soil water. There are gravitational water, capillary water, and hygroscopic water. Gravitational water is not held by the soil, because this water drains out freely due to the action of gravity. So that's why it is called as gravitational water. But capillary water is the water which is retained in the soil after the gravitational water gets drained off. And because of retaining capacity, capillary water is the most useful or beneficial for plant growth, or we can say this is the available water for plant growth. And next is the hygroscopic water. This water is absorbed by the particles of dry soil and is held as a very thin film on the surface of soil particles. For example, say this as the soil particle, above which there is a thin film layer like this. This is called as hygroscopic water. This hygroscopic water cannot be removed easily from the soil particles as it is held by a soil moisture tension of 32 atmosphere. Soil moisture tension for hygroscopic water is around 32 atmospheric pressure, so that's why it cannot be removed that much easily. So that means this hygroscopic water is not available for plant use. So these are some types of classification of soil water, and 32 atmospheric pressure is the hygroscopic water for soil moisture tension. And in case of at PWP, that is permanent wilting point. What is permanent wilting point? The unavailability of moisture content for plant growth. That is a permanent wilting point. So we cannot use that water because that water is under the soil moisture tension of 7 to 32 atmospheric pressure, which is a huge one to be easily absorbed. So these are some points regarding duty and delta and water requirement of crops. Now we shall move on to next fifth question. So now fifth question is based on Kennedy's theory. We have to find the critical velocity in a channel having CVR, that is critical velocity ratio 1.1, discharges 50 Qmax, side slope of the trapezoidal channel is 1 horizontal to 2 vertical, or we can say 1 vertical to 0.5 horizontal, B by D ratio, that is width to depth ratio, as 2.5. So we have to calculate critical velocity in this trapezoidal channel using Kennedy's critical velocity formula. So here the answer is option C, 1.351 meter per second. So we have to use this formula. Critical velocity is given by Kennedy's theory. V0 is equal to 0.55 m d power 0.64. So here in this question, they have given this critical velocity ratio as 1.1. That is, m is equal to 1.1. But they didn't give a depth value in direct. B by D is 2.5, side slope they have given, and discharge they have given. So by using this data, we have to calculate small d. So for typical trapezoidal channel, we have these two formulas for area and perimeter. You can refer to this suggested video of OCF, open channel flow, in order to get the details on the calculations of a trapezoidal channel. So by using that calculation, we can get the value of small d. So after finding small d value, just substitute here d in meters, m is in 1.1, m is equal to 1.1, and just substitute d value so that we can get the value of critical velocity as 1.351 meter per second. So this is the basic and important formula regarding Kennedy's theory. By using V0 value, we have to calculate another velocity using Manning's equation. We have to compare that velocity using Manning's equation and this velocity, whether these two are matching or not. If at all it's not matching in the first trial, we have to go for second trial by changing the depth or by changing the dimensions of trapezoidal channel, like side slope or anything, B by D ratio, because we have to get a matching sequence of critical velocity using Kennedy's method and the velocity found by what, Manning's equation. So this is how we have to calculate the velocity or to design the alluvial channels. Now we shall see other things like drawbacks of Kennedy's theory and what is a stable channel. And stable channel is nothing but the channel which has neither silting nor cover. So that is called as stable channel. And there are many drawbacks of Kennedy's theory. We shall see one by one. First one is there is no equation for regime velocity. Kennedy does not consider any regime conditions. So that's why no equation for regime velocity. The velocity is based only on the depth of flow. There is no other variable parameter here. We can see in this formula. Only d is the variable parameter. M is m is arbitrary. We can use in practical, like if at all it is coarse sand, we can use 1.1, which is arbitrary. There is no method to calculate m. So no method to find what critical velocity ratio, that is m. There is no specific regime slope, and eddies in the sides are ignored. Eddies formed in the sides of channel are ignored. So these are the drawbacks of Kennedy's theory. But these drawbacks are mostly overcome by Lacey's theory. Now we shall see in the next question the Lacey's theory. Now let's see the Lacey's theory question. The three independent equations in Lacey's theory are, so option A, AF square is equal to 140 V power 5, where V is velocity, A is area of flow, F is Salinity factor. So option B, C, D. So there are three options are correct. So this is somewhat MSQ type question, multiple select question. We have to select three options among the four to get the three independent equations in Lacey's theory. So first three options are the correct for three independent equations in Lacey's theory. So first, AF square is equal to 140 V power 5, V is equal to 10.8, R power 2 by 3, S power 1 by 3. Here S power 1 by 3, not 1 by 2, as in Manning's equation. R is equal to 5 by 2, V square by F. Now we shall see other more important formulas for design of channels in or design of alluvial canals using Lacey's theory. So this is the velocity formula, qf square by 140 power 1 by 6. And f is the silt factor, 1.76 root of d mm. D is the diameter or size of silt particles that should be substituted here in mm. So dmm. So that means this silt factor has some meaning because we are calculating on the basis of diameter of the silt particles. So this is not empirical or this is not arbitrary. So that arbitrary value of m in Kennedy's theory is overcome by using this silt factor, and we are considering the r here. Well, in the velocity formula you can see here r is the hydraulic mean depth. Hydraulic mean depth is the variable parameter here. Unlike in Kennedy's theory we are using only the depth of flow as the variable parameter, since v naught is equal to 0.55 m d power 0.64. And now next is the perimeter. Wetted perimeter is the 4.75 root q, and hydraulic mean depth, that is 5 by 2 v square by f, and s is the side slope. Yes, 5 by 3 divided by 3340 q power 1 by 6. So these are the formulas. Actually this is not the side slope, this is the longitudinal slope, this is not the slide slope, sorry. S is the longitudinal slope. S is equal to 5, f power 5 by 3 divided by 3340 q power 1 by 6. So these are the basic and important formulas for designing a canal using Lacey's theory. And V has to be substituted in meter per second, Q in meter cube per second, and perimeter in meters, and what else? R should be in meter. This is how we have to substitute all the data so that we can get the correct answer. And there is something called Lacey's cover depth that will be given by using this relation, 1.35 into q square by f power 1 by 3. Here q is in small letters, that means discharge per unit width. Discharge per unit width, that is capital Q divided by unit width. So that is nothing but small q. 1.35 into q square by f power 1 by 3, that is cube root. And we shall now see the merits of Lacey's theory. So Lacey considered one regime section for discharge and silt factor. So that is a overcome or advantage for Lacey's theory. Lacey correlated F to size of silt. So we have seen in this formula F is equal to 1.76 root of dmm. So Lacey correlated the silt factor to the size of silt. So that means it is not arbitrary. This is independent of rugosity coefficient. The velocity calculated is independent of rugosity coefficient. Why? In Kennedy's theory, we have to compare the critical velocity with the velocity that was found by Manning's equation. Manning's equation in which we have rugosity coefficient. Here there is nothing to do with Manning's equation, so that's why velocity is independent of rugosity coefficient. So that is a merit of Lacey's theory. And next, hydraulic mean depth as the relevant variable. So here you can see the velocity depends on hydraulic mean depth. But in case of Kennedy's theory, velocity depends only on the depth of flow, that is small d. And here Lacey considered semi-elliptical section. But in Kennedy's theory, he considered only the trapezoidal normal section. Here there are three regimes: initial, final, and true regime. True regime is nothing but a channel shall be in regime if there is neither silting nor scouring. This is the true regime. Initial regime means the first stage of regime obtained by a channel after it is in service. That is the initial regime. In this initial regime case, with increase in bed slope, only the depth varies but not the width. That is the advantage of initial regime. With the increase in bed slope, only the depth varies but not the width or the size of channel. Channel obtains the stability by varying only depth and bed slopes in the initial regime. So in initial regime, only the depth matters or depth varies. Depth width of the channel does not vary. In case of final regime, this is nothing but the ultimate stage of regime attained by a channel when in addition to the slopes, we have the freedom to adjust the width of channel as well. See, we have no adjustment to width of the channel in case of initial regime, but in case of final regime, that is the ultimate stage of regime obtained by channel, we can adjust the width of the channel as well. So that is the regime concept in Lacey's theory: initial, final, and true regime. True regime is nothing but there is neither silting nor scarring. And Lacey's theory is applicable to both channels and rivers, but Kennedy's theory is applicable only to channels. And there are, in spite of many merits of Lacey's theory, there are some drawbacks of Lacey's theory. We shall see that. True regime not achieved in actual practice. True regime means what? There will be neither silting nor covering. That will be not achieved in actual practice. That is a drawback, or that is actually difficult to achieve. And there are different values of f. For one f value will be considered only because of d, but there can be different values of silt factor because soil can be of any type, clay, sand, or anything. So that's why there can be of silt factors of many values, different values. So that's a drawback. And these formulas v, f, p, r, s, these are highly empirical one, not dimensionally correct. These are highly empirical. There's some small drawback in Lacey's theory. And the silt charge and silt grade are not defined properly. What actually is the silt charge? Silt charge is nothing but weight of silt per unit volume of water. Again repeating, silt charge is nothing but weight of silt per unit volume of water. In case of silt grade means type and size of silt. Silt grade means we are not considering the gradation. We are considering only the type and size of silt. But these definitions are not defined properly while arriving these formulas in Lacey's theory. So these are some drawbacks of Lacey's theory. Now we shall move on to seventh question. Seventh question is based on the analysis of gravity dam. So they have asked the hydrodynamic pressure due to earthquake acts at a height of. So you can see here in this diagram, hydrodynamic pressure diagram due to earthquake. So they have asked this pressure value lies at a distance, what distance above the base or below the base, that we have to find out. So option A is 3h by 4 pi above the base. Option B 4h by 3 pi above the base. C 3h by 4 pi below the base or above the base. So option B is correct. 4h by 3 pi above the base. That is this distance. This distance is nothing but 4h by 3 pi. H is nothing but total height of the gravity dam. Now we shall see more about it. Before moving to this diagram, like this wave pressure diagram, we shall see more about other formulas in this diagram also. So here you can see the uplift pressure diagram. So due to uplift, there will be some pressure. So that will be calculated using this formula. W into H dash. H dash is the tailwater depth plus 1 third of H minus H dash. So because of drainage gallery here, the variation is like this. Without drainage gallery, the variation will be like this. Because of drainage gallery only, there is some fluctuation here. Like drainage gallery will dissipate the pressure, dissipate the uplift pressure. So that's why we are using drainage gallery. So this is one of the forces acting in the gravity dam. And the most important or main pressure is the water pressure acting horizontally on the gravity dam. So that is given by the horizontal component and vertical component. This is the vertical component or vertical column which exerts pressure over this slant surface, and horizontal pressure is given here. That will be acting at h by 3 because this pressure distribution is hydrostatic. And next is the earthquake pressure that we know. Earthquake has horizontal and vertical forces. So horizontal we have to use alpha h as the coefficient, and if in case of vertical we have to use alpha v. So that is given by uh, earthquake load. So these are some of the forces acting on the gravity dam. Apart from that, ice pressure and wave pressure, silt pressure also there. Here you can see silt pressure diagram. Because of silt deposits on the upstream of the dam, there will be some pressure due to silt that will be given by half into gamma HA square into Ka because of active earth pressure. So that is why Ka we are using, that is nothing but 1 minus sine phi by 1 plus sine phi, where phi is the what angle of internal friction of the silt. Now we shall see the wave pressure by using this diagram. Here you can see the wave height, that is Hw. Hw is given as 0.032 root of Vf, where V is the velocity of wave and F is the fetch. Fetch is greater than 32 km. We can use this wave height formula. So here in this diagram itself is self-explanatory to show what is the HW, where the pressure force acts. Pressure force acts at 3 by 8 of HW from the water surface, and pressure acts, that is small pw acts at HW by 8 from the water surface, and that value is given as 2.4 gamma W HW. This is the pressure and this is the pressure force. Pressure force is nothing but 19.62 HW square. So these are some points regarding analysis of gravity dam. Now we shall see also the elementary profile of the gravity dam. So in an elementary profile of a dam having empty reservoir condition, vertical stress at heels and toe respectively are given by what? So here you can see in this diagram where is the heel and where is the toe. So at heel, what is the vertical stress in case of empty reservoir condition? And at toe, what will be the vertical stress in case of empty reservoir? That is, there is no water in the upstream side of the dam. So here the answer is option C, 2W by B at heel and 0 vertical stress at toe. Now we shall see more points regarding elementary profile of a dam. The slope of elementary profile, that is this one. This is the slope of elementary profile that is similar to hydrostatic pressure distribution. So we have seen the hydrostatic pressure distribution as like this, triangular hydrostatic pressure distribution. In the same way, elementary profile is constructed. When the reservoir is empty, only the self weight of the dam, that is sigma W, acts. Summation W. Self weight acts at a distance B by 3 from the heel of the dam. So P max is 2W by B and P minimum. There is no tension. That's why at toe vertical stress is 0. In case of reservoir full condition, that means there is a water up to the brim level, then there are two conditions. One is resultant should pass through lower middle third point, that is this middle third point, and next is the dam should be safe in sliding. So first we shall consider this resultant should pass through lower middle third point. By using that, we can get the answer for base width of the dam. So that is given by capital H divided by root of G minus C. So what is capital H? We know depth of water in the upstream side or the height of the dam. And what is G here? G is specific gravity of concrete, because we are considering only the concrete dam. So that's why we are calculating, or that's why we are using the specific gravity of concrete as G. Minus C. C means uplift pressure. Whatever the uplift pressure is there, we have to use that coefficient of uplift pressure as C. If there is no uplift pressure, then C will be 0. Okay. Then we have to consider the H and GC to find the base width. And next condition is regarding sliding. Sliding we have nu, that is what that is nu is nothing but the friction or the sliding factor. So H by nu into G minus C. By using this also we have to find the base width. Whichever condition is critical, we have to consider that base width. So next we shall see the stability requirements. So first is the overturning. FOS for overturning shall be more than 1.5, and that is nothing but ratio of resisting moment to the ratio of overturning moment. Resisting moment will be given by the dam. Overturning moment will be given by the external forces such as water pressure, earthquake, etc. And next is the sliding FOS. Due to sliding, what is the factor of safety we have to give? Nu into vertical force divided by summation of horizontal forces. And there is another thing called shear friction factor. This will be given when the dam has very large base width. So that's why shear friction factor is given as nu summation V plus BQ divided by summation H. So and apart from all the things, this is the basic and important formula. P max or P minimum is equal to sigma V divided by B into 1 plus or minus 6E by B. So here E is the eccentricity of loading, and that E has shall be B by 6, so that there will be no tension. We have to avoid tension in the dam profile so that we can reduce the cracks. Because of tension there will be cracks. Because of cracks there will be less area of compression. So because of less area of compression, the dam may fail prior to the compression requirement. So that's why E is equal to B by 6 is the basic thing we have to remember, so that P minimum shall always be 0. P minimum shall always be 0. So here you can see, so this diagram based on reservoir full condition, and this is for reservoir empty condition. In case of reservoir full condition, there will be P minimum in heel portion and P max in toe portion, and that's why resultant will pass to the lower or upper middle third, we can say this middle third. In case of empty condition, lower middle third or at nearer to heel, the resultant will pass. If the resultant is away from the dam body, then the dam may be failing because of P minimum. So P minimum shall not be there. If at all there will be there is a P minimum, that value shall be very less. So that is the main criteria regarding the stability of gravity dams. Now we shall see the ninth question, which is based on Khosla's exit gradient. So here we are on a permeable foundation with the downstream sheath pile is shown. So here you have to refer the figure to find the details to get the value of exit gradient as per Khosla's method. So this is one important and most repeatedly asked formula and asked question in various examination, a most important concept in Khosla's exit gradient. So all the details has to be got from this diagram only, so that we can get the answer as 1 in 4.34 as the exit gradient. So here you can see the formula. Khosala's exit gradient is G is equal to H by D into 1 by pi root lambda. So what is lambda? Lambda is equal to 1 plus root of 1 plus alpha squared by 2, and alpha is B by D. So here the point is to find the B value, and D is nothing but the depth of downstream sheath pile. So that is nothing but 8 meter. They have already given in the diagram. So D is 8 meter. So what is B? B is the total horizontal length. Horizontal length. So we have horizontal length AB as 20 meter, and we have horizontal length CD as 25 meter. But we don't know the horizontal length between B and C. So that has to be found. That is the main thing here. So horizontal length AB plus between BC plus CD. So 20 plus 25 plus BC horizontal length. But we know only the slant length of BC. So what is horizontal length of BC here? BC slant length is 5 meter, and the difference between vertical difference between B and C is 3. because here you can see 11 meter here, 8 meter here. 11 minus 8 is 3. So here 3. So what is this horizontal distance? 4, by using simple Pythagoras theorem. So 20 plus 4 plus 25 gives the answer for horizontal length or horizontal creep length as 49 meter. So we know the value of b, we know the value of small d, and just substitute here for alpha value, and whatever and the value got for lambda is here, and we know what is h. H is nothing but the level difference between upstream side and downstream side. Here upstream side is mentioned here, and in downstream side there is no water present. So that means the depth from the permeable foundation or the depth from the permeable foundation only from this to the this value. So that means 11 meter is the capital H. We should not substitute H as 8 meter because there is no water in the downstream side. So that's why we have to calculate from the base of permeable foundation of the weir in the downstream side. That is nothing but H, capital H is 11 meter. So the data has to be substituted properly to get the answer for Khosla's exit gradient as 194.34. So these are the important things regarding Khosla's exit gradient. Now we shall see more about other theories like Blake's creep theory and Lenz's weighted creep theory. In Blake's creep theory, we have creep length as horizontal length plus 2 into vertical length. So this is the vertical length and this is the horizontal length. Horizontal length has to be as such, and we have to multiply by a factor of 2 for vertical length to calculate the creep length. So hydraulic gradient we know h by L. So that shall be less than or equal to 1 by C. C is creep coefficient. And we have to calculate the thickness of concrete floor. So this is the concrete floor. Here you can see. So this is the concrete floor, the thickness of which has to be calculated on the basis of the head over that floor. So T is equal to 4 by 3 H by G minus 1. This 4 by 3 is nothing but factor of safety only, nothing else. Factor of safety we are adopting as 4 by 3. And H is the unbalanced head. For example, we have to calculate the thickness of concrete bed at here. Then we have to find the unbalanced head at here by using this formula. H is the level difference between upstream and downstream side, and 1 minus L1 by L. L we know the total creep length. What is L1? The creep length up to here. Up to here, what is the creep length? That is L1. So by using this relation, we can find the unbalanced head. So just substitute here G H by G minus 1. G is the gravity of concrete. So by using this, thickness of concrete floor is given as 4 by 3 H by J minus 1. And next is the Lenz's weighted creep theory. Here only one change, that nothing but for horizontal length we have to use 1 by 3 as multiplying factor. That is the only weighted creep theory for Lenz's weighted creep theory. So apart from this, in case of Khosala's exit gradient, we are using D value, that is depth of downstream pile value. So what if there is no pile in the downstream side? This pile is absent, which means exit gradient will become infinity. So what that directly means is, if there is no downstream pile, there will be infinite exit gradient. That is, we have to construct downstream pile in order to avoid, in order to lessen the Khosala's exit gradient. So downstream pile is must needed in case of Khosala's creep theory. Now we shall see the last question. The type of canal alignment which involves the maximum cross drainage works is option A ridge canal, option B contour canal, option C canal crossing, option D side slope canal. So which is that canal which involves maximum CD works? CD works means like canal siphon passage, like that. We shall see more about it. So contour canal is the type of canal alignment which involves maximum cross drainage works. So that's why contour canal has to be like avoided because of maximum cross drainage works, which involves expensive constructions. So we shall see one by one the cross drainage work. So first one is the aqueduct. Aqueduct means the canal will be above the drain. So HFL of drain is below the bed of the canal. So here you can see HFL of drain is here, but bed of the canal is here. So this is called as aqueduct. So this is also a aqueduct, but HFL of drain is above the canal bed. So here is the canal bed, but above the canal bed only HFL of drain is there. So that will be called as siphon aqueduct. This is one type of CD work, that is canal above drain. And next is the drain above canal. Here two types of there. Here also FSL, that is full supply level of canal, will be much below than the bed level of drain. Then that will be called as super passage. In case of FSL of canal above the bed of drain, then that will be called as canal siphon. So this is a canal siphon. Now we shall see other thing also. One is this is the level crossing, in which the level between drain and canal are the same. The drain and canal are at the same level. They will mix each other, and we using cross regulator and drain regulator, we can regulate the flow of the canal and drain. And this is canal inlet and outlet. This is also a type of cross drainage. And next we shall see some construction in canal. So this is a type of like a canal fall, which is used to control bed grade. So in order to avoid the erosion in bed grade, we have to construct canal fall. So this is a type of canal fall. And this is head regulator, or we can say canal regulator. Canal regulator is constructed to control the flow depth. This is a type of canal escape, a weir canal escape. This canal escape is constructed to control the FSL. This canal FSL has to be controlled, right? So to control the full supply level of canal, we are constructing the canal escapes. Here natural drain will be there. And other things such as canal outlets and modules are also constructed to control the discharge from the canals. So these are the some cross drainage works and canal construction or structures to control bed grade, flow depth, discharge and FSL. And we are at the end of this video. If you like this video, please comment, share and share with your friends. And we have left some of the concepts like spillways, dam spillways also. We can cover those things in the upcoming videos. Please stay tuned. Thank you for watching. You can watch these suggested videos also, and please comment your views below. Thank you.